So as you're opening to page 12, we'll just remind ourselves that project number 7 is currently assigned. We're about to give a big old hint for part of this project because it has to do with probability, and I know that probability isn't covered maybe as much as it might be in the high school math curriculum. So project 7 is there. It's due on April 24th. I continue to forget to think about how to fix the quiz and project being at the same time. So today we'll talk about something called the integral test. Next class are a couple more tests and lots of tests as we go through some stuff about series. So we'll get there. But let's take a look on page 12, and we're going to give a big hint about the project. So we're going to answer a problem that is related. It's different, but related to something in the project. So, Tastic, can you read number 1? Okay, so we were talking about guns and violence. Let's call these paintball guns. There's really just, right, nobody's dying here. So here's the idea. We've got gunslinger A is going to go first, and so I'm going to start this at the bottom, start down here. Okay, so it's A's turn to shoot, and A is either going to hit or miss. So if A hits, I'm going to draw a branch for both of these two things. So if A hits, we're going up. If A misses, we're going to the right. What's the probability that A hits on any given shot? It's 40%. So put a 40% right there. And if A hits, then the game ends. As soon as somebody hits, the game ends. So 40% of the time, A is going to win this game on the very first shot. Yeah? Which means what's the probability that A misses? It's 60. So 60% of the time, is A going to lose? The game just continues, right? If A misses, then it's B's turn to fire. This is a very civilized gunfight where they take turns, right? So now it's B's turn, so B will be here in purple. And B is either going to hit or miss. And what's the probability that B hits? That's 70%. And if we land up there at the top, then what's the outcome of the game? B wins. What's the probability that B misses? It's 30%, right? 70% win, 30% lose. So 30% of the time we go over here. And what happens if we get over to this blue dot? Now it's A's turn, and we just play the same game again. It's not clear whether the thing will converge. It certainly could go forever, right? If both of these guys miss forever, this game would last forever. So there is some infinite thing happening here. But convergence or divergence, we have to wait and see. Okay, can you guys draw, I would like you to draw another few branches of this. I want us to get over to this spot right here. Can you fill in some of the blanks? I want to eventually get to that next time when A will win. So there's a blank in there that you fill in, and then next time. Put hits, put misses, put percentages, and then write down who wins at the top. So see if you guys can fill in, and then we'll do some calculations. Okay, so I filled in, and again, in theory, this could go forever to the right. But every one of these dots up at the top here represents a completed game. And so, for example, if I was trying to get to this dot right here, what happened first? A missed. I mean, there's only one branch that will get you to that dot. It's this and then this. It's the only way to get up there. So we know that first A missed, and then B missed, and then A missed again. I should have an A there. And then B missed. And finally, oh, that's it. And then finally, oh, actually, B didn't miss. What did B do? B hit, because we had the jut up there at the end. So what if I wanted to know what's the probability that I actually follow this particular yellow path here? Well, what's the probability that A missed on the first one? 60%. And then following that A missing, we need B to miss. And anybody know what we do with these percentages to find the probability that we go along the path? Is we multiply them. If you have one thing happening, followed by another thing, you multiply those probabilities together. So the probability that A misses is 60%, and then the probability that B misses is 30%, we're going to multiply. 60 times 30, there's an 18% chance that we end up following. I'm doing that right? Yeah, 18% chance that we follow that bottom path. 60% and then 30%. And then we need A to miss, that's another times 60%, and then we need B to hit times 70%. And if you multiply those four percentages along that yellow path, you will find the probability that B wins in exactly this particular game. 60 times 30 times 60 times 70, all is percentages. Okay, so the ultimate question that we're trying to answer here is, what's the probability that the first gunslinger wins? So we're just focusing on A, we don't have to worry about B at all. So we need A to win in the first round. What's the probability that A just wins on the first shot? 40%. But just as good, A could win on its second shot, A's second shot. So how do we get A to win on its second shot? In this case, we're trying to get to here. So what numbers do we multiply to get to there? That's good. 0.6, 0.3, 0.4. That's how we get up to there. So I'll write down 60% times 30% times 40%. And if you multiply them together, what do we get? 18, 4, is that 0.07, 7.2%? Okay, so 7.2% of all the games that happen, A is going to win right there on its second shot. And if we didn't allow the game to go any further, what would you do to find the probability that A wins in either the first round or the second round? You'd add these two together, right? 40% of the time A is going to win outright. 7.2% A will win on the second shot. A is already going to win 47.2% of those games, plus some more. So we're going to add these guys up. Let's write down one more. Third round. So if A is going to win on its third shot, we need to get up to that outcome circled in black. So what are we multiplying? Yeah, all the way to the last one. Everybody hear that? Okay, that's exactly how we get to that last one there. So we go 60 times 30 times 60 times 30 times 40. Somebody give me a number there. How much? 1.3%. And it's not likely that they're going to keep missing, right? I mean, that's why the percentages here are going down. What I'm calling the second round is A's second shot. Yeah, I should have been clear about that. A's second shot. Okay, and so then we bring all these numbers together, and we'll write down this. The probability that A wins anytime, meaning could be the first round, could be the second round, could be the 18th round if we get there, is equal to the sum of these numbers over here. So it's 40%. I'm going to start writing these as decimals. 0.4 plus, and then the next one is a 0.6 times 0.3 times 0.4 plus 0.6 times 0.3 times 0.6 times 0.3 times 0.4 plus, and then it goes forever. Yeah, so the question is, do we have information that we can figure out what this is equal to forever? So let's give people a moment to copy. Everybody see where those numbers come from? And so what's it called when you add infinitely many numbers? The series. Series can either converge if it goes to a single finite number, or it can diverge if it goes to infinity. In this case, well, it's not really clear. What's happening to these blue numbers as we follow down? They're getting smaller, so at least there's a chance, right? It looks like these numbers are going to 0, so there's a chance, but it is by no means guaranteed. Just because the numbers go to 0 doesn't mean the total sum forever is finite. Yeah. Yeah, what kind of a series is this? This is a geometric series. Can you identify what the common ratio is? What do you multiply each term by to get the next term? Yeah, it's 0.6 times 0.3. Yeah, 0.4 is just sitting there. Got a 0.6 times 0.3, that's times the previous term. And then I have a 0.6 times 0.3 times the entire previous term. And every time it's a 0.6 times 0.3, because you need A to miss and then you need B to miss. 0.6, 0.3. So that is a geometric series, and we know everything there is to know about geometric series. If that magic multiplier is small, very close to 0, then the thing converges, and we have a formula that tells us what it converges to. So the magic ratio here is 0.6 times 0.3, which is 0.18. Is that between -1 and 1? Yes, so this guy converges. And we can tell what it converges to. So the geometric series with the common ratio equal to 0.18, that's 0.6 times 0.3. And because that's less than 1, the geometric series converges, and we've got a fancy formula. What's the formula? A over 1 minus x, thank you. Remember, A is the starting term. What is it? It's 0.4 divided by 1 minus the common ratio, 0.18. It's just a hair under 50%. Anybody have a number for us? 8.8. So this game is just about a 50-50 even game. Even though B is a really good shot, right? 70% of the time B is going to hit. And A is only 40% of the time. But what makes this basically even? A gets to go first. In fact, of the 48.8% of the time that A wins, what part of that does A win on the very first shot? Is the 40%, right? Almost, if A misses on the first shot, A is probably not going to win. Right? 40% of the time A is going to win on the first shot. If A misses, there's only another 8.8% of the games that that A will win. Most likely it will end right on the next shot. B is going to hit 70% of the time. Okay, so probably not all of us have had a chance to look at the project, but I'm hoping that this will help with the project. So there are a couple of things happening. We had this big long decision tree. It went forever, but the idea is if you want to follow one yellow path, what do you do with the probabilities? Multiply them, and then if you want to look at all the different paths, what do you do with the probabilities? You add them up together, okay? And you're going to end up doing that on the project. Any questions on this? Okay, so let's go down to let's go down to number 2, Dawn.
All that a series converges if the sum.
All its terms.
All its terms.
Good. Okay, we'll go to the next part here. Chris? Okay, so we're gonna do this together instead of in groups, but let's write out the first 5 terms of each of these. So we know sigma notation means add. The first one starts at n equals 1. You plug n equals 1 into the expression, which is n, you get 1. Sigma means add. Then you bump n up to the next integer, and we get 2, and 3, and 4, and 5, forever. Anybody have any questions on writing out those terms? Okay, so we play the same game here. Plug n equals 1 in, what do we get? We get 1. Plug n equals 2 in, we get a half. Write out the next 3 terms. Sigma is reminding us of an integral, and today we're covering something called the integral test. But sigma just means add up all these things. Yeah. What's the next term? 1/3, and 1/4, and 1/5, forever. And then we do the same thing here, but now we're plugging into 1 over n squared. When n is 1, 1. When n is 2, is 1/4. When n is 3, 1/9. Everybody understand? Plugging in. Okay, and then part D, this is 1/2 to the n minus 1. First plug in n equals 1. 1/2 to the 0, which is 1, so the first term here is also 1. Then plug in n equals 2, and it's 1/2 to the 1, which is just a half. When n is 3, that's 1/2 to what power? To the second. So that's 1/4. Next one. 1/8. 1/16, etc. Okay, so we've got 4 different series here. The goal for today and for the next several classes is just to decide if the series is finite when you add forever or infinite when you add forever. Those are the 2 choices. And we're a little bit spoiled by starting with geometric series, because for geometric series, not only can we say it's finite or infinite, but we can actually figure out what it adds up to if it's finite. It added up to 48.8% on the last one. That is very atypical to actually be able to figure out what the thing adds up to. We're going to content ourselves by saying it's finite or it's infinite, and that's it, right? Most of the time we have no hope of saying, oh, and it's 48.8% when you add it all up. Okay, one of these guys, when you add forever, is clearly infinite. Which one is that? A. Okay, so this guy up here will say diverges, and diverges very badly. What makes it so that the other 3 at least have a chance to converge to something finite? Is the terms are getting smaller and they're approaching what number? 0, right? In all the other 3, the individual terms are approaching 0, which means maybe it has a chance of converging. But if the terms don't go to 0, there's no chance at all. And so that guy right there has a name. We're here at number 3. Garrett?
The one series above that is converging all tails what I call n term that's
of a sub n not equal 0, then the sum from 1 to infinity of a.
Okay, so this a sub n business, a sub n is our generic name for what's inside of the summation. So in the example of this last one here, a sub n is equal to 1/2 to the n minus 1. Okay, a sub n is just our generic term sitting inside of the summation. Now for this one, if I take a limit as n goes to infinity of these terms, 1/2 to the n minus 1, what happens to those terms when you plug in bigger and bigger n's? They approach 0, right? 1/2, 1/4, 1/8, 1/16. So those ones go to 0. But for the first example, part A at the top, what is the general term? It's n, right? We were looking at the summation of just n. And is this equal to 0? No, what is this equal to? It's infinity, which is kind of overkill. I'm just going to say it's not 0. That's all that we need. I could give you one where, what if I had this summation of something like 2 plus 1 over n? Yeah, when n gets really big, what do the terms approach? They approach 2. And if I ask you to add infinitely many 2's, what are you going to get? Infinity, right? So yeah, so it was kind of overkill that the first terms, not only were they not going to 0, they were actually getting bigger. Doesn't need to be the case, just needs to be not 0. So the first one diverges, nth term test. And we can just write that as a little sentence. Diverges since limit as n goes to infinity of n, the terms themselves are not 0. And this is our nth term test. For divergence. Yeah. Good question. Okay, so we'll answer that. Any questions about the language here? Fails the nth term test for divergence. Okay, so Don asks a very good question. For this summation of 2 plus 1 over n, does it converge to 2 or does the thing diverge? The answer is both. It depends on what you're talking about. And so we got to be really clear what it is that we are talking about. These guys, as a sequence of numbers, as a list of numbers, what do they approach? The sequence here approaches what? 2. A perfectly good number. So I would say the sequence converges to 2. But then the series where you add all of those 2's up is infinity. So the sequence approaches 2. Maybe I'll even change the word approaches and change it to converges to 2. But the entire thing, the series, diverges. And that's a really important distinction, so I'm glad we have that question in front of us. Is it clear the difference between the two? The list of numbers gets closer and closer to 2. It's a perfectly well-behaved list of numbers. But then if I decide I'm going to add all those numbers up, that isn't well-behaved at all. It goes to infinity. Okay, so we saw part A definitely diverges. One of these things definitely converges. Which one of these have we seen? Have we seen 1 over n squared? Yeah, the last one. So the 1 over n squared, we've seen something like that. We haven't seen that in series vocabulary, but we'll come back to 1 over n squared. But what kind of a series is part D? That's a geometric. It's an exponential. And somebody mentioned during the group thing yesterday, last class, is every exponential a geometric? Yes. So the definition of a geometric is you keep multiplying by the same thing. That's what an exponential function does. Is every step to the right on an exponential function, you multiply by the base, the same thing. So this bottom one here is geometric. with the common ratio of, what do you multiply by every time? 1/2. 1/2 is definitely less than what magic number? 1, that's the cutoff for geometric series. So this one converges. We can find the sum. Yep. Okay, the two in the middle, B and C, are the ones that are unknown at this point. We've got adding up the 1 over n's, and then we've got adding up 1 over n squared. So just a real quick game. What if I told you that part B was finite? If I add that up forever, what do you think you can say about the sum in part C? It's finite. How come? It's smaller, right? I mean, like 1/4, this 1/4 right here is there, plus some other terms that aren't there. So if the top one is finite, then the bottom one is even more finite, if that makes sense. And then there's the other direction of it. Which one, if I told you one of them was infinity, which one would you like me to tell you is infinity? Is the n squared. Because if I tell you that the n squared thing, this guy adds up to infinity, what can you say about the top one? It's even more infinity, right? So it's the same kind of thing from the comparison test for integrals. All right, but right now we don't know what either of these things does. So we'll come down here to number 4, and we're over to Joe. Okay, so we're not going to do all of these, but let's let's just do part B here for a second. So S sub 1 is just the very first term in the list. What is the first term in this list? Is 1. S sub 2 is the sum of the first two terms. The first terms were 1 and 1/2. Yes? So that's 1.5. So once in a while, the smartboard just puts like extra dots near where I'm touching it. Like I promise you, I'm not like just jittery this morning. S sub 3 is the sum of the first three terms. 1 plus 1/2 plus 1/3. So is that like 1.83? And what we're doing here is we're turning an infinite sum, which is very difficult to comprehend, into a list of numbers, which is far easier to think about. If this list of numbers appears to level off somewhere, like let's say they keep getting closer and closer to 2, but they never get there, then it feels like we've got a convergent series, that the series goes up to, it adds up to 2. But if you keep adding these numbers and they get bigger and bigger and bigger, we get past 2, we get past 10, we get past 100. If I add enough of these things up, then what does it feel like is true about the series? That probably is infinity, right? And so we're just converting the hard, what does it mean to add up infinitely many things, to an easier, let's just look at the list of numbers here and decide what it appears to be doing. Okay, so that is that. Let's go on to number 5. Moving on to past number 5. Let's go on to number 6. We'll go back to Cole. Cole? Okay, so that's an important statement right there. It says the terms can go to 0 and still the series actually goes to infinity if you add forever. So we're looking at this sum of 1 over n. We've seen it already today. 1/2 plus 1/3 plus 1/4. It's called the harmonic series. The word harmonic has to do with music, harmonies. So overtones of a vibrating string have wavelengths that are these fractions of the fundamental wavelengths of the string. That's about all I know about that. Can somebody more musically inclined say anything? Do these words mean something to folks? Mm-hmm.
We don't know how to describe it, but it's definitely.
Yeah. So you guys have talked about wavelengths in physics, right? So it's the same kind of thing. If you have a guitar string and you pluck it, it's going to oscillate way faster than we can see. So we just see this kind of like shaded in thing when you pluck a guitar string. But if you were really able to slow it down with like this really high powered camera, you would see wavelengths, you know, like it would be several waves running along this guitar string and you'd see them with different lengths. And somehow if you were able to put your finger on a different fret and make the wavelength half of what it used to be, you will get something called an overtone. And if you make it a third of what it originally was, you'll get another overtone. And so that's why we call it the harmonic series, because it has to do with harmony and music. Okay, part C. What is the limit of a sub n, as n goes to infinity, for this harmonic series? So first let's write out what it actually is. Limit n goes to infinity. A sub n, remember, is our generic name for the term in the series. What's the general term in this series? What's the thing inside of the sigma? It's 1 over n. So that's what we're asking about. What is this equal to? It's equal to 0, right? The terms go to 0. But then we'll get to the sad part of today, Sam, despite. Some? Yeah, if you take a look at 1 plus half plus a third plus a quarter forever, turns out it will get to infinity. It will take a long time to get to infinity, but it gets past 10 if you add enough terms. It gets past 100. Probably would take more than a lifetime to add enough terms to get it to be up to 100, but it will get there. So we're going to prove this using something called the integral test, and we're going to continue to write complete sentences with all these tests. So here's what we're going to do. We're going to change gears, forget about that summation, the 1 plus a half plus a third. Temporarily, we're just going to think about this integral of 1 over x dx. Okay, so 1 over x is that graph right there. The integral, we know, represents an area under the curve. From where to where? From 1 to infinity. So I'm just going to maybe kind of trace out this part right here. And 1 over x, that particular integral was one in our list of useful integrals for comparison. Anybody happen to remember? Does that one converge or diverge? That one diverges. That was the cutoff, actually. We had something generally something like this. 1 over x to the, was it n or p? P? 1 to infinity. And it converged if p was what? Less than 1? All right, so 1 is the cutoff. So what's the good side of 1? Yeah, because you want, if you want it to converge, you want lots of stuff on the bottom. So the fraction is close to 0. So if p is greater than 1, then that integral converged. We proved that way back when.
Which is really because you don't want the integral to be x.
Exactly, that's right. Okay, so what do we know to be true about that purple area forever? Okay, so we believe that. We proved that long ago. That area is infinity. It's just the cutoff one, but it's infinity. Okay, so now what we're going to do is we're going to approximate that area. We already know it's infinity, but we're going to approximate it by drawing in left rectangles. We're going to draw a left rectangle for every integer space. So between 1 and 2, if I'm drawing a left rectangle, which point do I pick? You pick 1, the left-hand point. You go up to the curve, you draw to the right, and you come down. Yes? That's the first left rectangle. Between 2 and 3, which one do you pick? 2. You go up to the curve at 2, go over to the right and down, up to the curve, to the right and down. It's probably enough. I want to write down the areas of these rectangles. What's the area of the first rectangle? It's 1, isn't it? Right? The base is 1 and the height is also 1. How about the second rectangle? The base is still 1. What's the height? It's a half, isn't it? Because this is the 1 over x curve, and because we picked between 2 and 3, we picked 2. 2 into that function is 1/2. So the area of this one is a half. The area of the next one is 1/3. So the green rectangles, if you add them up forever, that's a series that's so famous it has a name. What is that series called? That's the harmonic series. 1 plus a half plus a third plus forever. But we've already decided that the purple area, which is just under the curve, is infinity. So what do you think is true if you add up all those green rectangles? It's more infinity, right? It's a larger infinity. It's bigger than the purple area, which is already infinite. So here's what we know. We know that the sum of 1 over n equals 1 to infinity, is definitely greater than this integral. We're picking left rectangles because we want to get stuff bigger. It's going to turn out, we're going to pick right rectangles on the next problem, and then it's going to turn out, you don't have to ever think about which rectangle to pick. We're right now kind of building this test. But we buy it, right? This left-hand thing is the green rectangles. The right-hand thing is the purple area. I know that green is bigger than purple, and we also know that this one right here diverges, because that was one of our useful integrals for comparison. Therefore, what's true about the sum of 1 over n, it also diverges. I'm going to be lazy a lot of the time, and you're welcome to be lazy as well. Oftentimes, you don't even bother putting n equals 1 to infinity. It's just assumed. You know, certainly the infinity is assumed. Whether you start at n equals 1 or n equals 17 makes no difference, right? I mean, if it's infinity, it's not because of the first 17 terms. Okay, so this integral right here, that series diverges. And it is our first example of a very unfortunate phenomenon. What's true about the individual terms in the series? They approach 0. And sadly, what's true when you add up infinitely many of these things, which are just these little tiny wisps of numbers, you get infinity, okay? So from this point forward, you cannot assume that just because the terms go to 0, adding them up gives you something finite. It doesn't always work. Okay, so this proof right here, historically, I don't know exactly when this happened, say in the last 400 or 500 years, and that's a fairly recent thing. But you know, maybe 800 or 900 years ago, people actually knew, before they had any sense of an integral in calculus, they knew that this series right here diverged. And so here's a much easier proof that the series diverges. I'm going to group these things in a very special way. I'm going to group the 1/3 and a quarter. I'm going to group 1/5 up to 1/8. I'm going to group 1/9 up to 1/16, and I'll keep grouping so that we'll have twice as many terms in every subsequent set of parentheses, all right? And here's what we'll say. This is definitely, okay, so I'm going to put the 1 and the half, I'm ignoring those. But would you guys agree that 1/3 is definitely more than 1/2? Yes? Yeah. And I apologize. Definitely more than 1/4. Yes, 1/3 is more than a quarter. And the quarter, I'm just going to copy right there. So the only thing I've done is traded in my 1/3 for something which is a little bit smaller than a third. And now I'm going to go to the next set of parentheses. And I'm going to say that in this next set of parentheses here in blue, every one of those terms is Definitely more than 1/8, except the last one, which is equal, yeah? So then I can say this is more than 1/8 plus 1/8 plus 1/8, and then plus the only one that's actually equal is the last one. Yes. And everybody in the yellow parentheses is more than who? It's all more than 1/16. I won't write them all out, but we'll just say plus 1/16. How much is the first parentheses when you add the 2 quarters up? 1/2. When you add 4 1/8, 1/2. When you add 16, sorry, you add 8 1/16 is 1/2.
Thank you. I feel like something that's so much.
What do you get when you add? I can keep grouping and I can keep finding things that are always more than 1/2. What will I get if I do this forever? Infinity. I'm adding infinitely many halves. And the thing that we started with is definitely more than this thing, which is clearly infinity. All right, so that's kind of like a one-trick pony. I mean, the thing we did with the integral is much more useful than this thing here. But I just wanted to point out there's kind of a clean way to show it's definitely infinity. Okay, so when we're ready, we'll move to the next page. Number 10, and we're back to Maggie. Okay, thank you. So this time I'm going to look at, now we're going to look at 1 over x squared. And again, this was in our useful integrals for comparison list. So the area in this case, again, is from 1 to infinity. And I'll shade here in purple. And what do we recall about that purple area forever? It's finite. I don't know what it is, but I know that purple is definitely finite. Right? We saw that before. Okay. So last time Dawn wondered why we use left rectangles. Hopefully it'll become clear as soon as we use right rectangles for this one. So between 1 and 2, we're picking right rectangles. Which point do you choose? You pick 2, the right-hand point. You go up to the curve, and then you go left to draw your rectangle. Between 2 and 3, which point? You pick 3. You go up at 3. You go over. I'm already having trouble drawing these things. They're significantly smaller than the ones that we drew before. I'm not going to bother trying to draw the last one. I think my pixels are too big to draw the one at 4. But let's go ahead and write down the area of this first rectangle. What is the base of that rectangle? Is 1. The height was determined at 2, and the function is 1 over x squared. So what's the height? It's 1 over 4, right? 1 over 2 squared. So the area of that rectangle right there is 1/4. This next one, I was barely able to draw. Here the height was determined at 3. What's the area of that rectangle? It's 1/9. I'll write down one more area. I didn't draw the rectangle. Which point would we have used? 4. What's the area at 4? It's 1/16. And those are terms that we wrote down earlier today when we looked at that series, the 1 over n squared series. I'll just put it up here. What was the first term? Plug in n equals 1, we get 1 plus, and then I got right 1/4, and then 1/9, and then 1/16. Okay, so there's a little funny business happening, right? The 1 in the blue isn't down here as any of our rectangles, but ignoring the 1, again, what do we know about the purple area? It's finite. What about the green, therefore, forever? It's smaller than this finite purple number, right? So if you add the greens forever, what kind of a number do we get? Something finite. Does the +1 bother you? If I add all of these guys up, I get something finite. Add 1, it's still finite, right? So it makes no difference that we kind of ignored the very first rectangle. In this case, it's definitely finite. What's that? You can, but that guy's outside of this integral that we talked about. We went from 1 to infinity. Yeah, and there's a problem up here if we kept thinking about the curve that it goes up to infinity. So we don't draw that first one, and it doesn't bother us. Okay, so then I think we can write down some things that are true here. We can say that the sum of 1 over n squared from n equals 1 to infinity. Okay, so I'm going to write a little detail that I'll never write again, and I won't ask you to write. But would you agree this is the same as the sum of 1 plus 1 over n squared starting at n equals 2? Is that fair? All I'm doing is rewriting it like I did up here at the top. I'm peeling off the first term and then writing the rest of it in sigma notation. And that series is represented by which color, the purple or the green? That's represented by the green. We've got the green numbers written down below. And we know green is definitely less than purple. So this is definitely less than 1 plus the integral of 1 over x squared. It might bother some folks to see this guy starts at n equals 2, but the integral has a lower limit of 1. Those two numbers don't have to have anything to do with each other. Don't just copy it over here. I mean, the integral started at 1 because that's what our useful integrals for comparison list did. Okay, and then what do we know about this guy? That one is definitely finite. We saw that weeks ago. So then the series is also finite. So the sum of 1 over n squared converges.
You're saying there's not
If you are brilliant, like Leonhard Euler was, then you can figure out what it converged to. Great question. Let's come back to that momentarily. Any questions on the thought process here? Okay, let's first address Dawn's question. On the previous example, we used left rectangles because I was comparing to an integral that I knew was infinite, and so I wanted my rectangles to be above the curve. Here, I want to compare to something that's finite. I want to draw some that are below. The good news here is that it makes no difference. I mean, whichever way you need it to work, it will work by picking the correct rectangle. So we're never going to bother even worrying about which rectangle to pick. So we'll quote the integral test, and we'll talk about that after we answer these questions about, Euler and how did he prove what the sum actually goes to. So let me pull up a main Excel sheet that will list a few of the terms. So here it is, class 28. Okay, so this column right here is just counting. This column right here is doing what? It's squaring the first column. So the first column is n, the second column is n squared. This column is 1 over n squared, right? So if you look at 1 over 4, it's 0.25. So that's just the 1 over n squared. Now what am I going to do? What's the ultimate goal with the numbers in this column? We're adding them up. That's what this problem is add up the 1 over n squared. Anybody understand where the 1.25 comes from? Yeah, it's the sum of the, all right, so I need to use my mouse. It's the sum of these two guys right here is 1.25. And then the sum of those three is 1.361. So column D is just my partial sums list. It's just a cumulative tally so far. And so, so this guy right here, if I, maybe I can get some more decimals, that's good. So if I scroll down, this is the thing that we're looking at. Does this appear to converge to a number? So now we're 1.63, slowly 1.64. I'll scroll way, way down here. 1.6449. So that's after 72,000 terms. So it appears to be kind of leveling off someplace. And then Leonhard Euler, who's this brilliant Swiss mathematician from the 18th century, figured out that the sum goes to pi squared over 6. Pi squared over 6. So if the sum goes to pi squared over 6, and I want to build pi from that number, essentially I'm looking at the sum is somehow miraculously equal to pi squared over 6. What would I do to solve this for pi? Times it by 6, so 6s is pi squared, and then square root. So the square root of 6 times the sum is what I did in the last column. So take a look right here. It's probably too small for the folks in the back, but this says the square root of 6 times that number. So it's, and the next one is the square root of 6 times that number. And so what should we be seeing here in column E if Euler is right? We should see pi. Okay, so right here we are up to 3.13, and then we keep scrolling, and eventually we get to 3.1. See, and it takes longer, right? You get excited in the beginning because it goes quicker in the beginning. But of course, all right, so finally 3.14, that was after about 600 terms. What's, anybody know the next digit of pi? It's 3.141. All right, so I'm going to stop with the mouse wheel and we're going to grab over here. All right, there's 3.141. 5. 3.1415, yeah. 9. 6, 7, 8. You see how long it takes, right? Okay, so you can see the tiny changes that are happening as you go down, right? We're in whatever spot that 3 is, and eventually it turned into a 4. And eventually that will kick up and bring this guy into a 9, but it's going to take a long time. This was 100,000 terms, and we got up to 3.14158. Close. So I am fairly certain that there is that the way that Euler figured out what it goes to, this pi squared over 6, I think it is in a book which is marvelous and very readable called Journey Through Genius by William Dunham. It's in the Western Mass Library System. I'll write it over here. I'll write it on the smart board. Journey Through Genius is largely a math history book, but it's got enough math in it to keep you entertained. And I think that this is one of the proofs that's in this book.
Take everyone's favorite subjects together.
William Dunham. I think that proof is in there. And if it's in there, it's readable. Everything in that book is readable. Yeah. This proof is in there? The book is readable. Yeah. Task today, you don't happen to remember offhand if this was... Right. Right. So now you can read it, and it'll have meaning. What's that? I don't remember. I remember reading this thing in the book and thinking, gosh, that's really smart. But I don't remember offhand what he did. It was not Excel. No. But could you imagine? I mean, just like faced with this number right here, even with Excel, how long would it take you to realize, oh, that's just pi squared over 6? It could have been.
What is the ratio of the circle radius to its circumference have to do with that series?
Yeah. What's that? Yeah, it should. It's not at all clear to me why pi has anything to do with that series. Sure, sound is a wave. Yeah, if the proof is there, it hopefully will give you some insight. Okay, so let's bring everything. That's a good question. I don't know. I'll look it up when we're doing something together. Okay, so let's conclude here with the integral test. So we've built this whole theory now. We're just going to write it up formally, which will give us a little bit of a shortcut into using it. So the integral test says, suppose that a sub n is equal to f of n. All right, so already that might look a little bit intimidating, but in our example that we just did, 1 over n squared was the terms. And what function did we think about the integral of? Didn't we think about 1 over x squared? So, you know, how about we just don't worry about the letter x, we'll call it n, right? So that's the tie-in there. And then we've got these conditions that we always need to check. We need two things to happen. We need f to be decreasing, and we need all the terms to be positive. F has to be decreasing and positive. Okay, let's come back up here and think about those two things. Okay, first of all, suppose that f was not an increasing function. It went down, it goes up, it goes down, it goes up. It could be something like that. The problem here, our left rectangle is always going to be above the curve. Our right rectangle is always going to be below the curve. The answer is no. So because sometimes the left rectangle is above and sometimes it's below, you can't just say, oh, the greens are always less than the purple area. And so we need the function to be decreasing so that the rectangles stay consistently either above or below. And then positive. So what if stuff were negative? Well, I guess we'd really be in trouble if it were negative. I mean, if you've got something that's decreasing and eventually gets negative, then it's going to get more and more negative forever as we go. It's not really a compelling reason, but I don't remember why negative's a problem. I mean, I suppose that, is it the same thing? Yeah, but as soon as you let it turn around, then it's not decreasing anymore. Yeah. Is it the same thing? Is it that if you let it go negative, is it true that sometimes the left rectangle is above and sometimes it's below? Left rectangle here is above, left rectangle here is, I don't know. We need it to be positive. We'll see how to handle stuff when there are negative terms, but that's not here. Okay, so we need those things to be true for all x greater than or equal to some number c. If a function is increasing for just a little while and then decreases forever, that's fine. It makes no difference what happens near the origin. It's the infinite part that we're worried about. And then here's the conclusion. If the integral converges, if there's finite area, then the sum also converges. And it happens that we want to pick right rectangles in that case, but it doesn't matter. We don't even have to specify. If the, I forgot the word if here. If the integral diverges, then so does the sum. That's the conclusion. So let's take a quick look at 13, where we'll use the integral test. Okay, the first thing I do whenever I see a new series is write out the first three terms, just to give me some sense of what's happening with the series. When we plug in n equals 1, we get 1 times e to the, is that negative n squared? Can't quite read it, yeah? So is that 1 e to the negative 1? Plus, now n is 2, 2 e to the negative 4. I'll write one more, 3 e to the negative 9. Okay, so I see a few terms. The very first question I ask myself once I've got a few terms is, are they going to 0? Because if they're not going to 0, then it diverges. Are those terms going to 0? No? What is it? It's a negative power on the e. Right, those e's are really downstairs. The 3 is up top. This, yeah, the bottom is, yeah. So they go to 0, which is bad news because that means we have more work to do. And is it a geometric series? Do we keep multiplying by the same number as we go to the right? Not at all. And so the only other tool we have right now is the one we just developed, this integral test. So I'm just going to write down a couple of things. You need to show that f of x equals x e to the minus x squared. All I'm doing is changing the n's to x's. We need to show that this is decreasing and positive. And to show a function is decreasing is a Calc 1 thing. So you'll end up taking a derivative to show that that function is always decreasing. It is. And then you need to find the integral of that function, x e to the minus x squared dx. And so you've got to go through the process of finding an antiderivative. And you also have to handle that infinity. How do we handle infinity on the integral? Call it b, and then let b go to infinity. So we haven't left these integrals here. You find this thing, and then you just write the conclusion. If the integral is finite, what about the series? It's finite. If the integral is infinite, what about the series? It's infinite. So we can write up some of these details. I know I'm over time here. We can write some of these next time, but those are the 3 steps for every application of the integral test.
Are there finite series? Like where if the integral converges and the sum diverge, but the integral converges.
I think they're one and the same. Yeah, because the rectangles didn't really care about which one was the focus. Like yeah, good question.